I'm Daniel Alfaro. I'm part of a team DRC-Hubo. Here I'm going to show you a portion of our C2 trailer. That's our command and control trailer. So this is the vehicle we're bringing to Miami. This is where we fix the robot out of. This is where we practice all of our events out of and control the robot out of. You can see this area right here. We have one of our Hubos that we're fixing up right now, doing some modifications on. This is our Hubo fixing station. Over here and down here we have all the parts we need to repair the robot, replace any broken or damaged parts, so we can continually have a functional robot as we go along. Right over here, this is a built-in gantry system. This can hold 3+ Hubos, so all we have to do is bring it up, attach them right here, and we can roll them all in and transport them easily, as well as work with them very nicely while we're in the trailer. So if we walk back here, we can see 2 control stations. This one right here is for monitoring the robot. An expert monitor will look at the robot's vitals, make sure everything's operating properly, and fix any errors as it goes along. This station right here is the control station 1. This is the primary controller, so the person doing the different tasks, such as valve turning, ladder climbing, etc., will be operating right here. And then back here, control station 2. This is our third command and control station. This is where the secondary operator, if needed, is applied. All these are hooked up to what we call HuNet. HuNet is our Hubo network. All you do is VPN into that from anywhere in the world, and then you act like you're on the Hubo network. Now, we're going to walk around the side of the vehicle for a moment. This right here is our full C2 trailer, our command and control trailer. You can see once we park, we can take our stuff out, then set up our camp or our workshop. So right here we have the DRC-Hubo robot. Right now we're working on stepping over a few cinder blocks. Again, this is the full trailer. This is everything that we need to compete with the DRC challenge. And this is one of our robots that just comes right out of the trailer, and then we can operate it immediately. This right here is our output to our robot, as well as the input to our trailer. Right here is our high amperage 220 volt input. This allows us to power the entire trailer over one input. So this includes all of our computers, networking, etc. We have a single cable that goes out to the robot over Ethernet. So this is what we can control the robot by via the DRC standards. Now, if we want to run completely wirelessly, we also have a wireless bridge that connects directly to the robot if we are running wirelessly. Again, DARPA standard wired network and the optional wireless. So right over here we have the back of the Hubo. We have 2 Ethernet connections, one here and one here. This is for the local Ethernet on the robot. So this allows us to talk to the LiDAR, any other computers we have hooked up. One is for the vision computer and one is for the control computer. These get put into a single switch that allows us to have a single Ethernet cable output. This can also attach to a wireless bridge as well. Again, that is 2 Ethernet connections, one for each of the computers, plus all the plus for the LiDAR and other sensors, and that can go out into one output Ethernet device for control. Here we have our Cisco, Netgear, and UBNT networking system. So this allows us to take in a single Ethernet input from the robot and control the bandwidth and the latency just like it will be in competition. Again, it's composed of 3 parts. It's controlled of a main controller that's run by Cisco systems, a switch run by Netgear, and a throttler run by the UBNT network systems. And that is our C2 command and control trailer for the DARPA Robot Challenge.
In this video, we present a supervision and teleoperation framework that allows an operator to monitor a robot in 3D, plan dual or single-arm manipulation tasks, preview the tasks in simulation, and finally execute on a real robot. This framework has been applied to the valve turning task of the DARPA Robotics Challenge. The framework has been implemented on the Hubo 2 Plus robot, the improved DRC-Hubo robot, and finally the Willow Garage PR2. By creating a robot that can perform industrial tasks such as opening and closing valves, it may be possible to avoid future disasters and mitigate the risk to human life. Turning a valve was difficult with the Hubo 2 Plus robot and required large whole-body movements that could throw the robot off balance. The new DRC-Hubo robot has an additional degree of freedom in each arm, which makes object manipulation significantly easier. We have created a user interface tool called localization markers, based off of interactive markers, to allow for the quick identification of objects in an unstructured environment. The size and shape of a localization marker can be modified during robot operation, and once a localization marker has been chosen, the operator can manually align it with a full 6 degrees of freedom or use the iterative closest point algorithm to snap it to a point cloud generated by the robot. We use the constrained bidirectional rapidly exploring random tree algorithm to quickly plan whole-body movements for the Hubo robot that avoid collisions and maintain constraints such as balance and closed-chain kinematics. Once the trajectories have been tested in both simulation and on the robot in an open environment, they are run on the robot using our test apparatus. The test apparatus consists of an off-the-shelf racing wheel that can be raised or lowered and tilted towards the robot. The amount of force required to turn the wheel can be modified in software to test for objects that require different amounts of force to manipulate. The framework handles a limited communication link to the robot by allowing the operator to modify data rates during operation in order to stay below a target bandwidth. The framework is generic and can be used to manipulate different objects that require different trajectories, such as a one-handed ball valve instead of a two-handed wheel valve. We would like to acknowledge the help of Hubo Lab and Rainbow Company at KAIST in designing the DRC-Hubo robot for this competition. If you are interested in any of the software seen in this video, please see our open source repositories at these addresses.
This video presents our preliminary work towards addressing the ladder climbing event in DRC DARPA Robotics Challenge using DRC-Hubo robot. This video clip shows DRC-Hubo is able to mount, climb, and dismount the ship ladder. DRC-Hubo is an upgraded version of Hubo 2 Plus with more flexible arms, powerful grippers, extended legs, and torque control support. The ship ladder used in the experiments is similar to DARPA's specification for the ladder to be tested in the challenge. Backward climbing strategy is chosen for better collision avoidance. The motion is finished in 7 minutes. Our approach has 2 major components: a primitive-based ladder climbing motion planner and a DRC-Hubo compliance controller. The planner takes ladder specifications and robot pose as input and outputs a collision-free and quasi-statically stable trajectory for execution. The compliance controller enables compliance on arm joints for error compensation. Motion primitives contain prior knowledge from humans' ladder climbing experience. The motion primitives, designed by human experts, are utilized as seeds to generate motions for new ladder environment. A motion primitive is used to solve for an action, for example, mount a hand on the rail and place one foot to a higher rung. Moreover, an action can be changing the robot pose to move the center of mass to the supporting foot for achieving balance. We tested our motion planner on various ladders in physical simulation, such as climbing an industry ladder without rails and climbing a vertical ladder. Motion robustness is tested in simulation by dropping balls of increasing mass onto a robot. We found the motion is robust to a 10 kg ball of speed 5.5 meters per second. The robot falls when the mass is increased to 15 kilograms, but we don't expect such large disturbances in practice. Errors from modeling, calibration, and controller affect the correctness of hand gripping on the rail. The climbing motion forms multiple closed chains which are sensitive to the errors. We developed a compliance controller which enables compliance on the arm joints to tolerate the errors. When fingers grip the rail, the compliant arm allows the hand position to be adjusted.
In this video, we present our ongoing work for the DARPA Robotics Challenge. Competitors in the DRC are expected to develop robotic systems capable of performing 8 simulated DRC events. We propose a model-based, semi-autonomous teleoperation framework using shared language to facilitate efficient supervised autonomy with low-fidelity communications. The language is for efficiently representing and exchanging knowledge between human operators and robots. The proposed framework has been implemented using a multi-process distributed software architecture for real-time control on a humanoid robot platform DRC-Hubo. One of the critical functionalities for humanoid robot is locomotion. We have implemented 2 locomotion modes, biped walking and quadruped walking. Perception is another critical component for robot autonomy. We have implemented a point cloud matching algorithm for object identification and pose estimation. We've also implemented a manipulation pipeline. The manipulation planner takes the grasp planes, a target and environment information as inputs, and returns a collision-free manipulation path. To validate our approach, we performed tests with 2 simplified DRC task scenarios on the model. For debris removal task, DRC-Hubo performs a sequence of primitive motions such as walking, grasping, and dual arm lifting. At the moment, this simple debris removal task takes longer than 10 minutes because the operator is relying only on limited visual feedback. We expect the task completion time will decrease as we add more autonomy to the robot and develop more efficient interface tools for the operator. The second scenario is the wall breaking task. For simplicity, the scenario is designed to test only perception and manipulation aspects of the task. The robot was able to grasp and lift the drill and move the tooltip along the target path successfully. In this work, we have proposed a robot control framework for the DRC. We showed preliminary implementation results with 2 simplified DRC scenarios, and the feasibility of our approach has been demonstrated successfully.